Hello viewers and my dear students. Welcome to session 4 on thermal analysis, that is demo on simple one-day heat conduction problem, typically called as furnace wall problem. This is the basic thing what everyone should know. That is why I covered 3 sessions on this, and the 4th session I think I'll be able to show you some more details regarding this particular problem. Okay. Now at the end of session 3 we were here. That means we have done the temperature plot. Okay. And it is 870 here, 40 here. Okay. And in between this is T1, this is T2, T3, T4. T2 we have found out as 750.82 theoretically, and also I have proved that using Ansys it is 750.82 anywhere on this line you get nodes, no, all nodes will on this line will have the same temperature 750.82, and all nodes on this line will have the same temperature 183.3 in that way. Okay. Now these things, basic things, anyway I can demonstrate once more. But before that, I'll apply the temperature gradient, how it varies. Now it is 800 here. By the time it should come here, it should be 40. And the thickness of this, this thickness of the first one is up till here, no? It is 0.135. Okay, 0.135. And next is 0.075. And next is 0.115. Totally amounting to 0.325 meters. 0.325 meters. Okay, anyway, one thing, path operations, you see here let us say plot elements I do. Okay, this you do. You have path operations, define path, by nodes you go, click the first node and click the last node, that is enough. First node and last node, in between you don't have to worry. Only if it is on the curvature, you have to select all the nodes. First node and the last node you select. Okay. Say OK. And you give it as BG1. Okay. You just then BG1, the number of sets and all that you get. Anyway. Then once you do this, map onto path you do. Once you do the map onto path, you want temperature only. Okay. Temperature. Okay. You just say OK. Then plot path item on graph, you take temperature only, because we are interested only in temperature between this point and this point. Just say OK. Then you see here beautifully it has given at the end, no, 870 it will be. Okay. And at this, as you know, if you add up all the thickness, it is 0.325. Okay. And at the end of that is first break, that is it is 0.135. At 0.135 somewhere here, 0.135 somewhere here, okay, 0.132 here, 0.135 somewhere here, the temperature is 750.82. It is perfectly, it is okay. Okay, 750.82, it is also okay. Then, and at the second brick layer, second thickness, at the end of second material, at the end of second material thickness, it is 0.21. At 0.21, after 0.188 somewhere here you should get, this is 0.21. Okay, at this, if you see, it is approximately 183, correct? No, somewhere here, if you go here, it is almost 183. In that way, and at the end, no, at the end it is, at the end of 3 layers, first layer, second layer, third layer, it is 0.325 is the thickness, at which point you exactly have 40 degrees centigrade. This is another very important graph, what you can't forget to show it to your examiner whether he asks or not. This is what everybody is impressed. If you show this, whether they ask you or not, this also you have to show. This will be a very good thing for you to do. Okay, now you see here, I have told you, see here, plot elements I'll do. Okay, plot elements, I'll go to the same thing. See here, In this, once you do this, you see a list. If you have any doubts, no, about properties of all materials. If you see 1.2, 0.14, 0.85. First material 1.2 and 0.14, 0.85. You can check it in that way. Okay, that you have done correctly. Then list loads, all solid model loads you put. Solid model loads if you put, line 4 will have 870, line 10 will have 40 degrees. See here, you see line 4 870, okay, line 10 40. Then if you want to see which is line 4 and all that, you go again, plot controls, numbering, you see here line numbers, no, line numbers you make it on. Line numbers you make it on. Okay, in this line numbers when you make it on, see here, once you make it line number on, if you see here, this is line 1. I think you can see line 1, line 2, line 10, line 3, line 7, line 11, in that way 5, 6, something like that. Okay, see carefully, it is line 4. I think it is line 4. You just see line 4, this is line 4. If you have any doubts, you expand this. Line 4, this should be line 4. This is line 4, 870. Line 10 is 40. I think correct, no? This is line 4. If you have any doubts, no, you can enlarge the area and see. Okay. Line 4 is this. I think it is correct. Line 4 is this. In that way, line 4 you have a temperature of 870 and line 10 you have a temperature of 40. In that way, it is proved that you have applied the boundary condition properly. See here, one more thing what I want to tell you here is the quantity of interest in structural analysis will be you are finding the stresses, you are finding the deformation plot and all that. Stresses and deformation in a simple way. But when it comes to thermal analysis, you should very well know the quantity of interest here is temperature and this small q, flux plot. Temperature plot, flux plot and vector plot are very important things by which you will know what exactly is flowing, what exactly is happening. That means heat flowing from high temperature to lower temperature region and all that. You can clearly view it in a vector plot and all that. Okay, heat flux plot you'll have, temperature plot and all that. These are all the quantities of interest, particularly in thermal analysis. Okay, now what I'll do, plot controls, numbering, line numbers off I'll do. I'll just say okay. Okay, now plot, multiplot. Okay, plot elements, if you do, it's that. Okay, now as you see here, anything, no, here you just see, if you just see plot nodes, you can see here how many nodes you have got, everything you'll get. Plot elements means all elements. Each one is an element. As you see here, here 10, 10, 10, 10, 10. In that way, 10 into 30 here. Here 10 into 30, 10 into 30. Okay, 300, 300, 900 elements you have. Okay, this 900 elements you have. Now you see here what I'll let us say, now you know very well 900 elements we have. If I want to reduce the number of elements, okay, if you want to reduce the number of elements, what I'll do is, okay, in case let us say they ask, okay, you say reduce elements number, it is taking too much of memory, it is taking too much of time to execute and all that. Then what you do is, okay, you go here, okay, under preprocessor you go, okay, under mesh, no, mesh, size controls, lines, okay, picket lines, no, picket lines you take, here, here, here and here, picket lines you take, okay, you make it initially at 30, no, Now you make it as 10. Okay, you make it as 10. Did you follow? Now actually you see here, it was 30 here, I made it as 10 only. Then what I'll do, mesh, areas, free, pick all I'll do. They say, this already mesh, but do you want to remesh them? Yes, I want to remesh because earlier I had made 30 elements here. Now I have converted to 10 elements. That's why I want to remesh again. Okay, yes. Then you see here beautifully. See here, instead here also 10, 10, 10. Here also instead of 30, it has become only 10 only. Okay, instead of 30. Now the from the fine mesh, it has becomes the coarse mesh. Okay. Now you see here. Now once you do this, if you see this list, loads, the solid model loads and all that, on 4 and 10 the load is still remaining. You don't have to worry at all. Okay, load is remaining. Now what I'll do is solution, solve, current ls I'll do. Okay, now solution is done, you got it. Now if you do general post process, same thing you do. Plot results, contour plot, nodal solution, nodal temperature, you get the same thing. Okay, and then nodal solution, and I told you thermal flux is very important. You should get it as actually 1059. Okay, 1059.34. Okay, for this also not much of a change. Okay, instead of coarse mesh, I have made instead of fine mesh, I made a coarse mesh. Now I have told you in this particular session how to remesh. That means you meshed already. It will be very fine mesh. Let us say if it is taking too much time, you can make it coarse mesh in this way. This is one of the things. Okay, once you do this, I have told you plot controls. Plot control that is using this. No, once you know this, plot controls, numbering, node numbers on. If you do, you get so many things. Okay, see here, you have got the node numbers and all that. Anywhere here, anywhere on this line, you take the node numbers. Okay, anywhere on this, you have the node numbers. No, all these node numbers and all these node numbers here on this. Okay, you should have 750.82 and all these node numbers should have 183.3. That means what you should do is list results, nodal solution, temperature you do, and you see that all this you just see what are all the nodes you have on this, and see here what are all the nodes on this line. You should have 750.82. What are all the nodes you have on this line? You should have 183.3. Okay, in that way you are able to solve a very good basic problem in 1D conduction. Okay, and also in plot results, this vector plot also you see predefined and beautifully it has given you only 10. No, this is 1059.34 watt per meter square. This is the heat lost to the surroundings, watt per meter square, because it is not Q, it is small q, Q by A, watt per meter square. It is the heat lost to the surrounding. Now we have come to the end of this session. Thank you very much for watching. Thank you, friends. Thank you.